All right, implicit differentiation. Things you'd like me to go through with respect to implicit differentiation, any problems? Ever cause some mystery to your world? There's a lot with implicit differentiation, probably the more, I don't know, that tends to be a little bit more involved when dealing with implicit, because you can have your product rules, chain rules, quotient rules that go into implicit differentiation. As we talked about yesterday, the key thing to remember is you still follow all your properties and laws or rules of derivatives, but when you're dealing with that, you want to tag along. When you're dealing with the y variable, you want to tag along at dy dx. And that's ultimately what you want to solve for, is dy dx as you go through the problem. So you need to solve for that, and sometimes that takes a little bit of manipulation to be able to solve that. Implicit differentiation gets involved. I understand that. Any problems you need me to get through? Solutions are provided for you, so hopefully you work these solutions, and questions that you may have, you may be able to answer as you look at my solutions, just to help you out a little bit. All good, huh? For now. The problem we start running into is when all these things, as everything in my classes, when you start putting them all together, is you have to make an adjustment in regards to, first off, you have to evaluate, what do I have to use here first, and then apply the rules. Because today what we get to work with is logarithms.
My favorite.
Logarithms. We want to determine dy dx for the ln of x. Let's start out with that one there. How do we determine that? Well, if we would go limits as t is approaching x of ln of t minus ln of x over t minus x, doesn't help us out too much. If I would try to limit as h approaches 0 of ln of x plus h minus ln of x all over h, doesn't really help us out too much. So how do we deal with the logarithms? How do we deal with the ln's? Well, what we do know is some properties of logarithms. Well, if I have an ln, the ln is a log base e of x. That is your ln, your natural log is log base e. Well, if I have log base e, this, once again, as we're going through logarithms right now in pre-calc. Logarithms tend to be that mystery operation that we don't use very much. So we're not as comfortable with it or familiar with it. So let's take it out of the logarithmic form into an exponential form. How can we rewrite log base e of x equal to y?
E to the y equals x.
E to the y is equal to x. E to the y is equal to x. Our base is e, our exponent is y, our value is x. And let's use our technique that we utilized yesterday. That's implicitly differentiate. So let's take the derivatives of the left-hand side. Well, the derivative of the left-hand side, well, if I take the derivative of e dy, how do I take the derivative of e's? just the same thing. So we have e to the y, but then we had to take the derivative of our exponent, which means that's going to give us a dy dx. So we recopy, then we take the derivative of the exponent, that's the derivative of y. The derivative of y is dy dx, is equal to the derivative of the right-hand side. Well, what's the derivative of x? 1. So this now solve for dy dx. Well, if we solve for dy dx, we can divide both sides by e to the y. So we have dy dx is equal to 1 over e to the y. Oops, yeah, e to the y. Well, the whole premise of this started out was y is equal to the ln of x. So let's make a substitution. So we have 1 over e to the ln of x. Well, e to the ln of x is equal to what? X. So when we have y is equal to ln of x, the derivative of the ln of x is 1 over x. So then we have the chain rule for the ln, for natural log. Is 1 over f of x times the derivative of the inside, f prime at x. So if we have y equals ln of 5x, and we want to determine the derivative. We're taking the ln of 5x, so we have 1 over 5x times its derivative of 5x times 5. Well, we have 5 and the 5 that will cancel out. That will take us back to 1 over x. Ln's tend to be a little bit easier than implicit. So if we have ln of x squared plus 6, take your derivative. Jack, what do you come up with?
2x over x squared plus 6.
That's correct. 2x over x squared plus 6. We have 1 over x squared plus 6 times the derivative of x squared plus 6, which is 2x. So we have 2x times 1 over x squared plus 6, or 2x over x squared plus 6. Well, what if we have y equals log base 10 of x? We want to take the derivative of the log. Unfortunately, natural logs are a lot easier to work with than just regular logarithms. But if we follow the same method of madness, we can rewrite this 10 to the y is equal to x. And we want to find our derivative. Well, if we implicitly differentiate, we have a problem because if I had e to the y, the derivative of e to the y is just e to the y. Well, the derivative of 10 to the y is just not 10 to the y, unfortunately. Drats. But if we take the ln of both sides, what can we do with this exponent? Bring it up front. So we have y times ln of 10 is equal to ln of x. If we divide both sides by ln of 10. Now, ln of 10 is just a number. If I would clickety-clack into my calculator, ln of 10, I would get a value. So it's just a number. So this is just like having a coefficient. So rather than writing it like this, let's write this as 1 over ln of 10 times ln of x. Because 1 over ln of 10 is just a number. I can find that number. Now we're in a form that we can utilize to be able to find our derivative. Because this is just a coefficient. This is 1 over ln of 10 times the derivative of ln of x. Well, the derivative of ln of x is 1 over x. So we're equal to 1 over x ln of 10. Now, once again, you can leave it in that form, and that is fine. You get to books, you may look in books, they may sit there and say, well, I have x times ln of 10. They'll say this is 1 over ln of 10 to the x power. Is equal to my derivative. I'm fine with this. Once again, I'll show off your ability to manipulate logarithms. Go for it. But the key here is to get it into a form that we can work with. Follow the same method of madness. First, rewrite it in a form that we can work with. So let's get it out of the logarithmic form into an exponential form. So we have 7 to the y is equal to 2x. Take the ln of both sides. Take your ln of both sides. Take your y out front. Divide by your ln of 7. Use that as a coefficient. Because once again, ln of 7 is just a number, so use it as a coefficient. 1 over ln of 7. Then we can take our derivative. A lot of times, students will get a little confused because there's a lot of preliminary work to get from here to here. And they say, I'm done. I've done what I needed to do. Yes, you have to a point, but you haven't finished the problem because you haven't taken the derivative yet. You still have the derivative to take. We take the derivative of ln of 2x, Todd, what do you come up with? I'm sorry, what?
2 times 1 over x.
2 times 1 over x, or 2 over x. We have 1 over 2x times the derivative of what's inside, which is what?
2.
So what happens with the 2's? They cancel. So those cancel. So we're left with 1 over x ln of 7. On the back side, do not worry about problem 7 and 8. Problem 7 and 8, don't worry about it. You can still do problem number 9. Huh? Oh yeah, you'll do that here. It's very easy. Like I said, to me, the pinnacle of differentiation is typically implicit differentiation.
Do you do anything different with like sines?
Hmm?
Do you have to do anything different with like sines and cosines or just like derivatives?
It's follow the same properties that we've dealt with. Okay, follow your same properties. So you take 1 over, when you have ln, you take 1 over whatever you have, times the derivative of whatever you're taking the ln of. Just follow your chain rule.